Good day to all of us. My name is Genesis Noliedo, and today I'll be discussing about performance of short transmission line. In this discussion, you will be able to know what is short transmission line, its equivalent circuit model, phasor diagram, ABCD constant, voltage regulation, and line efficiency. By the end of this discussion, we will be having a sample problem in order to make sure you retain most of the important parts of this lesson. The overhead transmission lines are classified as short, medium, and long length depending upon how the capacitance of the line is taken into account. Today, we will be focused on short transmission line. What is a short transmission line? A short transmission line is defined as a transmission line with an effective length less than 80 kilometers or 50 miles, with a voltage less than 69 kilovolts. And unlike medium transmission lines and long transmission lines, the line charging current is negligible. Hence, the shunt capacitance can be ignored. For short length, since the shunt capacitance of this line is neglected, the other parameters like electrical resistance and inductor are lumped. So these are the characteristics of a short transmission lines. The single-phase line and equivalent circuit model of the short transmission line are shown in Figure 1.1. The resistance R and the inductive reactance X represents the loop resistance and the loop inductance of the short transmission lines. So as I mentioned before, the resistance and inductance are lumped in short transmission lines. The end line where the load is connected is called the receiving end, and the end where the source of supplies is connected is known as the sending end. Therefore, we can say that BR is the voltage at the receiving end, BS is the voltage at the sending end, IR is the current at the receiving end, and IS is the current at the sending end. And the cosine angle of the receiving end is the power factor of the load, and the cosine angle at the sending end is the power factor of the sending end. The series impedance of the line is given as impedance equals to resistance plus reactance. In short transmission lines, the shunt conductance and shunt capacitance of the line are neglected. Hence, the current remains the same at all points. So practically, we can say that IS is equals to IR equals to I. So it means that the current at the sending end is equal to current at the receiving end, and the whole current on the short transmission lines are all equals. When working with balanced three-phase line, it is assumed that all the line given voltages are line-to-line values and all currents are line currents. Thus, for three-phase line calculation, real power per phase is equals to 1/3 multiplied by the total real power, and the reactive power per phase is equals to 1/3 multiplied by total reactive power. And for a balanced three-phase star-connected line, phase voltage is equals to 1 all over square root 3 multiplied by line voltage. Now we will tackle the phasor diagram of the short transmission line. The phasor diagram for a load of lagging power factor is shown in Figure 1.2. Let's start dissecting the diagram. The receiving end voltage VR can be taken as reference phasor. As you can see, it is represented by OA. For lagging power factor, current I always lag behind at the voltage receiving end VR by an angle of theta r, as you can see on the diagram. As shown in the diagram, OB is the current I. The voltage drop in the resistance of the line is equals to IR, and it is represented by the phasor SC. And as shown in the diagram, it is in phase with the current IOB, which is parallel. The voltage drop in the reactance of the line is IX, and phasor CD represented it. Since reactance is lead by 90 degrees, CD is drawn perpendicular to the current OB. Total impedance voltage drop IC is the phasor sum of the resistive and reactive voltage drop, and AD gives it in the diagram. OD is the sending end voltage Bs, and angle theta S is the power factor angle between the sending end voltage and current. And angle delta is the phase displacement between the angle of the voltages of sending end voltage and receiving end voltage. The magnitude of sending end voltage can be found from the right triangle OGD. I'll draw a separate triangle to represent it clearly. So, this will be the hypotenuse, which is the OD. The base will be the OG. And as for the height, this will be the GD. Now let's start deriving the sending end voltage by letting the sending end voltage equals to OD. First, we have to apply the Pythagorean theorem on the triangle. So, we will have the formula OD squared, since this is the hypotenuse, is equals to square root of the base and the height, summation. So, this will be OG squared plus GD squared. Based on the diagram, OG will be the summation of phasor OF and FG, and while GD is the GC and CD summation. Therefore, we will have OD squared is equals to OF plus FG squared plus GC plus CD squared. By substituting the values based on the phasor diagram, we have OD will be the BS, OF will be the BR cosine theta R, FG will be the IR, and as for the GC, this will be the BR sine theta R, and for the CD, this will be the IX. Substituting the values on the formula, we will have BS squared is equals to BR cosine theta R plus IR squared plus summation of BR sine theta R and IX squared. Therefore, the voltage sending end will be square root of summation of BR cosine theta plus IR squared plus summation of BR sine theta R and IX squared. As for the power factor of the load, measured at the sending end voltage, cosine theta S is equals to OG plus OD. Substituting OG, which is OF plus FG all over OD. So, basing on the phasor diagram, we will have cosine theta S is equals to BR cosine theta R plus IR over BS. Now we will take the voltage receiving end BR as the reference phasor. Then we will have voltage receiving end is equals to voltage receiving end angle 0 or BR plus J0. And for the current, we have three scenarios: the lagging power factor, the leading power factor, and the unity power factor. For the lagging power factor, the current will be I angle negative theta r or I cosine theta r minus Ji sine theta r. As you can see, the angle for the lagging power factor is negative because the current is lagging behind by an angle theta r to voltage receiving end. Next is the leading power factor. The current will be I angle positive theta r or I cosine theta r plus Ji sine theta r. For this one, the angle is positive because in the leading power factor, the current is leading theta r on voltage receiving end. And lastly, the unity power factor. The current is equals to I angle 0 or I plus J0. As you notice, the angle here is 0 because the current and the voltage receiving end has no angle between them. As I mentioned earlier, impedance is the summation of resistance and reactance. And the sending end voltage will be voltage receiving end plus the multiplication of the impedance and the current. By substituting the values, we will have voltage receiving end plus resistance and reactance multiplied by I cosine theta r minus Ji sine theta r is equals to the voltage sending end. Simplifying it further, voltage sending end is equals to voltage receiving end plus IR cosine theta r plus IX sine theta r plus IR cosine theta r minus IX sine theta r. We can also derive the tangent delta that it is equals to IR cosine theta r minus IX sine theta r over BR plus IR cosine theta r plus IX sine theta r. And that's all the formula we can derive from the phasor diagram of a short transmission line. ABCD constant of a short line. The concept of ABCD parameters comes into play. Voltage and currents of the network can be represented as BS is equals to ABR plus BIR and IS is equals to CBR plus DIR, where A, B, C, and D are the different constant of the transmission network. If we put IR is equals to 0 at equation 1, we get constant A is equals to voltage sending end over voltage receiving end. Hence, A is the voltage impressed at the sending end per volt at the receiving end when receiving end is open. It is dimensionless. If we put BR is equal to 0 at equation 1, we get V is equals to Vs over IR. Hence, B indicates the impedance of the transmission line when the receiving terminals are short-circuited. This parameter is referred to as the transfer impedance. C is the currents in amperes in the sending end per volt on open circuited receiving end, and it has the dimension of admittance. Therefore, C is equals to IS over BR. And lastly, the D constant is the current in amperes into the sending end per amp on the short-circuited receiving end. It is also dimensionless. Therefore, we will have D is equals to IS all over IR. On the next slide, we will try to get the value of the A, B, C, D constant. We already know from the equivalent circuit model that the voltage sending end is equals to voltage receiving end plus the I or the current at the receiving end multiplied by the impedance, and the current at the sending end is equals to the I or the current at the receiving end. Comparing this equation with equation 1 and 2, we get that A is equals to 1, B is equals to C is equals to 0, and D is equal to 1. As we know, the constant A, B, C, D are mathematically related to a passive network. Therefore, AD minus BC is equals to 1. So, as I mentioned earlier, A will be 1, B is equals to C is equals to 0, and D is equals to 1. Voltage regulation. It is the change in voltage at the receiving end when the full load at a given power factor is removed, and the voltage at the sending end becomes constant. It can be written as at full load, BR at full load is equals to the voltage receiving end, and at no load, BR at no load is equals to the voltage sending end. Therefore, voltage regulation is equals to voltage receiving end at no load minus voltage at receiving end at full load over voltage at receiving end at full load. Or, simply, voltage regulation is equals to voltage at the sending end minus voltage at the receiving end over voltage at the receiving end per unit. Voltage or line regulation depends on the power factor. If the line has leading power factor, then the receiving end voltage is greater. And for lagging power factor, sending end voltage is greater. And lastly, we will discuss line efficiency. The ratio of power delivered at the receiving end to the power sent from the sending node is known as the efficiency of transmission line. For the efficiency of short transmission line, we will have to get first the power delivered to load, the power loss, and the power sent from supply end. The power from delivered to load is equals to P load BR I cosine theta R. Then for the power loss, P loss is equals to I squared multiplied by the R. Then for the power sent from the supply end, P send is equals to BR I cosine theta R plus I squared R. Therefore, we can say that the line efficiency formula is percent efficiency is equals to P load over P send times 100, or percent efficiency is equals to BR I cosine theta R all over BR I cosine theta R plus I squared multiplied by R. That will be all the lecture for short transmission line. In the next slide, we will be having a sample problems in order for us to retain what we have discussed today. Sample problems. Problem number 1. A three-phase, three-wire short transmission line has a resistance of 3 ohms and a reactance of 8 ohms per wire. At the receiving end, a balanced three-phase load throws a line current of 60 amperes at 13,500 volts line to line. 0.9 power factor lagging. Determine the voltage at the sending end, efficiency of the line, and the voltage regulation. In solving short transmission problem, it is highly recommended to take down the given parameters first. On this problem, we have the following parameters. Resistance of the line is equals to 3 ohms. Reactance of the line is equals to 8 ohms. The voltage receiving and line to line is equals to 13,500 kilovolts. The current on the line is 16 amperes. And lastly, the power factor is equal to 0.9 lagging. For this problem, we need to determine first the voltage sending end line to line. And as discussed earlier, we all know that the voltage sending end is equals to voltage receiving end plus the multiplication of impedance and receiving end current. First, we have to know the impedance of the line, where impedance is the lump of resistance and reactance. Therefore, the impedance on this problem is, say line is equals to 3 plus J8 ohms. When we convert it to polar form, we have say line is equals to 8.544 angle 69.444 ohms. Then we have to know the angle theta r. The formula for this is cosine theta r is equals to power factor. Therefore, theta r is equals to arc cosine of 0.9. Therefore, theta r is equals to 25.84 degrees. We all know at the short transmission line that the current at all points are equal. Therefore, the receiving current is equal to the sending current and the current of the line is also equal. Therefore, the receiving current is equals to 60 amperes. Now we will start to get the voltage sending end line to line. First, we must determine the voltage sending phase in order for us to know the voltage sending end line to line. Voltage sending end phase is equals to voltage receiving end phase plus multiplication of Z and IR. We all know that the voltage receiving end phase is equals to BR at the receiving end line to line all over square root of 3. By substituting it, we will have the formula voltage sending phase is equals to voltage receiving end line to line all over square root of 3 plus the multiplication of impedance and the current of the line. Therefore, the voltage sending phase is equals to 13,500 kilovolts all over square root of 3 plus 8.544 angle 69.44 multiplied by 60 angle negative 25.84. Take note that the angle here is used is negative because in our problem it is lagging. If it is leading, we have to use positive angle. Simplifying it more, BS space is equals to 7,794.228 plus 512.64 angle 43.6. Convert the 512.64 angle 43.6 to rectangular form. We will have 7,794.28 plus 371.24 plus J 353.526. Therefore, the rectangular form of our BS space will be 8,165.468 plus J 353.526. Convert it to the polar form, we have the BS space is equals to 8,173.117 angle 2.479. Now we have to get the voltage sending end line to line, which is equals to square root of 3 multiplied by the BS space. Therefore, voltage sending line to line is equals to square root of 3 multiplied by 8,173.117. The final answer will be 14,156.253 volts. And there you have it. We have get the voltage sending end line to line. On the next slide, we will solve for the efficiency of the line. For determining the efficiency of the line, we have this formula as discussed earlier. Percent efficiency is equals to BR I cosine theta R over BR I constant theta R plus I squared all over R. Since in our problem, the voltage receiving end line to line is the given, we have to convert it to voltage receiving end phase. So we will have BR line all over square root of 3 multiplied by I cosine theta R all over BR line over square root of 3 I cosine theta R plus I squared multiplied by the resistance. Substituting all the given values, we will have 13,500 all over square root of 3 multiplied by the 60 cosine of the theta, which is 25.84 all over 13,500 all over square root of 3, 60 cosine 2584 plus 60 squared multiplied by 3. Therefore, the percent efficiency is equals to 7,794.228 multiplied by 54 all over 7,794.228 multiplied by 54 plus 10,800. The final answer will be 97.498%. That is the percent efficiency of the line. Next, we will determine the voltage regulation of the line. For the last question, we will have to determine the voltage regulation of the line. For voltage regulation, we have discussed that voltage regulation is equals to voltage sending phase minus voltage receiving phase all over voltage receiving phase. By substituting the values on this formula, we will have the 8,173.117, which is the voltage sending phase, minus the 7,794.228 all over 7,794.228. We get the 794.228 from the BL 13,500 all over square root of 3. Therefore, the percent voltage regulation is equals to 4.861. And that will be all the answer on that problems. Thank you for listening on my discussion.